All right, hello everyone. Welcome to another episode of Quirkcast. This is your host Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel so you can match with us there. And then, as always, if you're on YouTube watching, post any questions or comments you might have during the episode so we can get to them. And lastly, it would be immensely beneficial for yourself and ourselves if you could rate and review the podcast wherever you listen to, if that's how you consume this information. So, I guess Mikey, let's get straight into it. I'm gonna go straight at you with this question. Um, my question for you is, what is a particle? And before we get to that, can you explain the history of like why this is not so obvious?
Yeah, I mean, I can explain the history, particularly like from my own standpoint, right? Like,
Mhm.
um, we like to look at the universe in terms of things we can count, right? Like, there's one Sahil, there's in a building with like 100 office rooms. Like our ability to kind of like stay sane in reality, like kind of relies on an ability to like count things, right? And particles are supposed to be like the thing that you can count, like how many particles are in Sahil. You hear like people talking about how many atoms are there in a person, and you can actually ascribe like a number to it. Um, and so that's kind of like, especially for me, that's kind of like how I grew up thinking about particles, right? Like most people learn that particles are these things you can count. But if you go a little further and you start studying particle physics, it's kind of like the whole education process is sort of like systematically breaking down this notion of the fact that particles are kind of these distinct things that you can count reliably, whose existence is, you know, um, concrete in some way. And I guess just like from a broader history, this comes from quantum mechanics, right? Like quantum mechanics, as some of you may know or may have heard, describes a probabilistic view of our universe. Um, but it's not just like the probability of an event occurring. It's not like the whether or not I go to the supermarket tomorrow is probabilistic. It's actually the existence of the particles in my body are also probabilistic. Everything is just kind of um, not well defined once you enter into the quantum realm. And yeah, I mean that's just like a brief overview of like super brief, like in terms of like why this is even a question worth asking. What the answer is, I think will probably take us a little more time to get into.
Yeah, I think so. My first exposure to particles was in classical mechanics, looking at things as point light particles with some sort of pairwise interaction between them. And then you have these set of equations in which you can simulate each time step, and it tells you how the system evolves given a certain set of initial conditions. But then when you go to quantum mechanics, it becomes more like a wave, as you were describing it, this sort of like probabilistic wave, or loosely speaking, that. And then how has, I guess, like, what is the significance of that? And then what is the significance of like other things beyond that? Maybe Tim, you might know, or Mikey, feel free to jump in.
Yeah, I think that's a very good connection to our everyday life experience, and also for those of you who may have taken like a class in science or physics, high school level physics. The way we tend to think of particles historically is, I guess, like Mikey said, it's kind of like, was it actually attributed to like Aristotle? Like they talk about the concept of atoms, where if you break things down at some point, it becomes indivisible, and then that unit of indivisibility is like the atom. And certainly we've discovered things like the atom, right? That seem to be small and indivisible, and that's why it seems like it seems like a good place to stop, right? And then you can define, hey, at some point things become so indivisible that whatever that thing that's left, we can count them, and those are the fundamental particles. And but unfortunately, kind of what we've been talking about, quantum physics kind of throw a wrench into this perspective. There becomes uncertainty, and these wave-like characteristics we'll go over soon. But further, there's actually another player, which is Einstein's theory of relativity. And the viewer might be familiar with this equation, E equals mc squared, right? And now it tells you that, oh, nice, very nice. It tells you that mass and energy is interchangeable That doesn't seem that all that crazy, but if you think about it, mass is a property of particle. And when mass and energy can be interchanged, it means that existences of particles can also be altered. And now, when you dig deeper and deeper, it's actually not so obvious anymore what a particle is, because particles, it turns out, can be created or destroyed, right? And when something, doesn't last forever and can be created or destroyed, and then it becomes, more interesting to ask just what is that something, right? Like, like it's and the concept of a particle is no longer the kind of the Aristotle idea. It's the thing that's indivisible. Well, it turns out no. If you can destroy create something, then it's not necessarily the absolute fundamental unit that cannot be divided.
Yeah, I think that's actually a good point to start with this. So there's a number of reasons why the idea of like a particle that exists continuously in time and can be reliably counted. There's a number of reasons why that's a problematic concept. And I think the most obvious one is the one that Tim just mentioned, which is the fact that particles can change. E equals mc squared, tells us, yeah, that a particle has a certain amount of energy, and you can say that there's a particle here, but that particle could spontaneously turn into just pure energy at any point in time, and then you no longer have a particle there. So when people count the number of particles in the universe, at best they're giving some kind of an approximate count, right? Because the number of particles is constantly changing. Particles are being created, particles are being destroyed, right? So that's the most obvious reason why counting them is problematic. If their existence is ephemeral, then it's not really a reliable counting number. And E equals mc squared is really just the beginning. I just wanted to put it out there. Like, one of the fundamental reasons why this concept is so problematic is, you can talk about like there's 2 protons here or there's 1 electron there, but from a physics perspective, they're all kind of made from the same stuff. The particle physics perspective is that there's just like, this kind of stuff permeating all of space and time, which we call quantum fields. And if you excite the quantum field that way, you get a proton. If you excite it this way, you get an electron. And it's just kind of a dance of the same material. So even particle species is not a well-defined thing. And we constantly observe particles, transitioning into other kinds of particles. And that brings an immediate problem to the idea.
So one thing I wanted to ask is, you mentioned that particles can change identity, which I agree with. Things like beta decay and other kinds of particle physics processes change one particle into another. Decay of a neutron into a proton, electron, antineutrino, if I'm not mistaken. So there's a way of how particles can change, and so your count's not reliable. I guess my question about this is that is there like, why would you say that it comes from the same thing? Like, what is the reasoning behind that? Like, why say if you excite it this way, it becomes this, if you excite it this way, it becomes this?
Okay, so that's fair. In a sense, you could argue that like my claim that they're all made from the same stuff is just dependent on my description of them as being the same stuff. And you were giving some concrete examples, like heavy particles can decay to lighter particles. And that's fine. We can still imagine that these particles have some concrete existence. But there's this, one of the most fundamental aspects of quantum mechanics is this thing called the uncertainty principle. And the uncertainty principle actually gives like a minimum amount of time over which you can track the conservation of energy. Below that time scale, conservation of energy is not a reliable fact. So if you see like a photon moving through space, at first it just appears to be moving through space like a single photon. But if you look really, really closely, like really, really closely on really short timescales, you'll see that photon is actually constantly turning into electron and anti-electron pairs and then recombining, and constantly like it's not even really a photon. It's got other stuff in it.
So one question about that, what does it mean to look really closely? Because if I take a magnifying glass and like look really closely, I don't know if I'll be able to detect like an electron anti-electron pair, electron positive pair. So how do you know that it becomes that way? Why is it just not a photon? Like,
Yeah.
what changes it?
how we know is a harder question, which I'll have to think about. But what I mean by looking closely is like looking at very short. Suppose you had like what are the best cameras now? What kind of resolution do they have in terms of how often they take frames? I'm not exactly sure. I guess probably in the gigahertz now. But if you had a camera that could take frames and pictures of the photon every 10 to the minus 32 seconds, then you would see this effect. You would see that this photon is not really a photon. It's changing into every other particle species that it can possibly change into all the time.
Yeah. So I think to understand this fact, maybe we should take a step back a little bit to understand, to kind of relate that to everyday lives, right? Like, what do we mean when people say, I see something? Like, let's say I see Sahil, and Sahil, you're made of particles, right? Your phase has protons, neutrons, and electrons in it, right? And
I would hope so.
yeah, and different proteins, lipids, whatever you call it, right? And I see it, like, how is that not real? I can take a piece of skin from you, look into the microscope, and there's stuff on it, right? When we do that, we're actually running a little bit of an experiment, right? And this experiment usually takes the form of some sort of interaction, right? If I poke it with I don't know, if I peel off some cells, look under the microscope, I'm shooting kind of different other types of particles at it, and kind of look at the reaction. Maybe it go into a computer, then it go into my eyes, so that I can observe it. And when that happens, there's often some sort of interaction, some sort of exchange of energy in order for this observation to happen, right? And the interesting thing is, for everyday interaction, it turns out we can roughly quantify the amount of energy that we use for those interactions. And those energy turns out to be quite small, right? From a fundamental physics perspective. They're really tiny energies. And what do I mean by that? By tiny, I mean the energy is so small that it doesn't tend to destroy or create particles. Like if a doctor check out Sahil's, your skin cells, they're not gonna blast some high energy gamma rays and just like create new particles out of it. No. It's just like a little gentle look under the microscope, right? So in that limit, a particle, it's a very simple object, right? It's a particle is just some unit of stuff that you can measure that is small and that's relatively point-like, right? But what Mikey is describing is more general framework, right? Like what happens when you move beyond this approximation, as opposed to just looking at things under like a really weak telescope using really small amounts of energy. Like what happens? And when we do that, things becomes murkier and murkier.
Well, actually, no. So you're talking about so when I was talking about the fact that a photon is turning into electron-positron pairs, right? I think what we're kind of referencing is the fact, like, how do we know that it's actually doing that? That's like he'll ask that question. It's kind of a tricky question because we can interrupt it during the process, or we can actually see that it's doing that. But then, how do you know that our interruption isn't the thing that caused, the splitting to happen? There's also, a very strong theoretical reason, which is if you assume that it's true, that it's constantly doing this, constantly like having this process of splitting and then recombining, splitting and recombining, that's actually a necessary step to getting the right answer in the calculations for things like how the photon propagates and all kinds of things like that. So I think it's a combination of experimental evidence and theoretical evidence. We know that this can happen because when we interrupt the process, we see it happening. But then, I don't know, Tim, what do you think? Is there any other evidence to the fact that we have this kind of, what we call a vacuum polarization diagram actually happens in real life?
I think that's fair. Like, it's almost like we can catch the particles shape shifting, basically.
Yeah, it's like if you could only see me every 5 seconds, and I was like making a funny face.
But I think it's fair to say that for something like the photon, this process is very, very rare, extraordinarily rare. I mean, not so extraordinarily rare, but rare enough that you normally don't have to worry about it, right? It's like 1 in 10,000 or something like that. And this
the environment, right?
right, of course, yeah. I would say in everyday environment, that's very rare, right? Like I'm looking at Sahil, I don't expect like a plasma of positron, electron popping out and then ruining the whole day. So I think that's fair. Of course, it depends on the environment. If you're near the surface of the sun, like that, the environment is way more hostile. But so that definition will probably not work anymore. But yeah, so I think that's fair, right? It's an environment dependent thing.
Yeah, it actually depends on the temperature, right? If the temperature is higher than the mass of electron positron, you'll see this. Oh, I guess that's how we know, right? We've actually seen photons in high temperature environments, right?
Yeah. So interestingly, our definition of a particle as this indivisible unit is also reliant on the fact that we live in like a cold, tough world in the universe. I know the Earth feels comfortable. It's like 300 give or take Celsius. Oh, sorry, Fahrenheit. No. Kelvin. My mistake. Like 25 degrees Celsius, give or take. But it's a pretty darn cold place compared to like I don't know, surface of the sun or like inside our Earth, right? So this coldness kind of freezes a lot of these fluctuations out, and that makes the definition slightly less approximate, I guess.
It's an illusion, yeah. The coldness of the temperature that we live in gives us the illusion that, particles, which I guess are ice in this analogy, this ice that we observe is actually a fundamental property of the universe. But you just bring up the temperature a little bit and you see that this whole picture goes to hell.
So you're saying it's a function of the temperature of the environment or the energy scale of the environment. Is that what we're saying?
A higher temperature makes it more probable that the kind of effects we're talking about will be observed, but they still happen. You can see their effect more when you crank up the temperature.
Huh. What are the different ways, even if they're non-obvious, of increasing temperature? Like, what are things that I can do to increase temperature?
All you have to do is increase the average energy of the photons in the environment, right?
I mean, it can also be electric field. I mean, temperature is just a proxy of the amount of interaction happening.
Okay, but when we talk about temperature of the universe, we generally ascribe it to photonic radiation, right?
Yeah, usually, but not necessarily.
Yeah, it's not strictly dependent on that, but in our universe, let's just go with that.
Yeah, no. Actually, there's a very good alternative example to show you how kind of ephemeral this idea of a particle is, how approximate it is, and this happens inside a piece of metal. I think. Like imagine, Sahil, you were tiny enough. Let's say you hop onto the magical yellow bus and shrink to the size of an atom. And you take a little detour inside like a hunk of metal, like, I don't know, what was a good metal? Aluminum, iron, or whatever, right? When you go into that environment, there's a lot of, what is it, nucleus, protons around, and neutrons around. And those protons will create a very strong electric field. And the closer you are, and the stronger the electric field is. And when you're inside that metal, this electric field is very pervasive. And the electric fields interact very strongly with electrons, right? And if you try to make an observation to these electrons, their properties actually change. They're not the electrons that you would observe normally because you're under such an extreme environment, I guess, in some ways. Just like if there was a higher temperature. And there's a buzzword for this in the realms of condensed matter physics. You don't call the electrons inside metal electron. I mean, you could. But these are generally called quasi-particles. And the behaviors of these emergent particles can differ significantly from normal electrons that you might expect. So that's one example.
Huh. So it's like a brand new particle just got created, or like rather a particle with new properties that are effective to describe the material got created from doing experiments.
Yeah, I guess it's a little hard to explain, right? Like these are, like you could call them electrons, but these are basically coming from the fact that atoms have a lot of electrons, right? A bunch of them. So these electrons jiggle left and right in a collective fashion, and especially in a metal, these electrons you can
Metals are
think
like
of
a
them.
gas. They're basically a gas.
Yeah, kind of like a gas, right? So they fluctuate around, and really we should think of these quasi new emergent particles as waves on top of this gas. Very similar to, I guess, like waves in water, right? We don't think of water waves as H2O. These are just fluctuations of the collection of H2O, but we don't think of them as H2O. Just like how the quasi electrons from a hunk of metal, we don't think of them as electron, even though we call it that. It's just I don't know, a collection of these electrons moving together left and right.
Huh. So I guess like would you also count sound waves to be quasi particles? I remember reading that there were like these things called phonons that describe sound waves in materials.
Yeah, I think that's a good segue into I'm not sure what, but no, but it definitely captures something like, like we talk about collective phenomenon, right? Or the kind of things that Tim's talking about. Like we're really talking about the simple example is like, uh, like uh, like water waves, right? Like water is made up of particles, right? And in principle, you can count the number of atoms like to some approximation, but then it can also form these uh, structures that we call waves. And that's what we would call a collective phenomenon. So what was I trying to go with this?
Well,
Wait,
Are
what-
are you saying like you could define more useful constructs from multiple of these individual units getting together and having a collective behavior that is easier or more useful to describe what you're trying to solve?
Yeah, but now I feel like we're kind of getting away because the whole point of this is like kind of is there such thing as a fundamental particle?
no,
Hmm.
I think it's fair to say that particles are a collective phenomenon because from the way the physics, the mathematics, the physics is described, this analogy is very apt because literally the mathematics tells you that particles are defined as collective motions of something called a quantum field.
Yeah, no, actually, that's a really good point. So, like the example I gave was actually awful, right? Like, so talking about water waves, right? We actually understand how water waves arise, right? There's particles that we consider to be fundamental in this model, and then when those particles move, you get something called a wave. But that wave is clearly not fundamental, right? It's being created by all this particle motion. But in quantum mechanics, it's actually it's balanced, right? Like the particles can be viewed as the collective behavior of the waves, and the waves can be viewed as the collective behavior of the particles. So it kind of balances things out.
Huh. But what happens? I remember when I was learning quantum mechanics, when you had a single particle, describing that as like a wave or this wave function. I don't know how much the analogy holds, but how would
Oh,
you
so yeah,
distinguish
yeah. You
between
can
that?
describe you can describe a single particle equivalently as a collection of an large number of waves. Um, so I mean
Oh,
that's essentially math. For those of you that don't know what a Fourier transform is, it's basically a statement that you can take a large number of waves and get a particle, or you can take a large number of particles and get a wave. I like to call it Fourier duality rather than wave particle duality, but
Yeah,
that's all.
I think basically, yeah. Once you add Einstein's equation in, you even forego the fact that particle numbers could change, and when that happens, they kind of just melt together, right? Like waves and particles are one and the same.
Yeah.
so taking a step back, and I mean taking a step back in time, actually, when the universe was much more dense and at a higher energy, and let's suppose you were there and you were trying to count particles, or like maybe you might see things pop in and out of existence, but would they still be the fundament? I'm going to use the loose term fundamental to describe our current fundamental, like standard model. Would you see those particles appearing, or would it be brand new? Would the particles just change identity completely because the environment's different?
It's a mix of both, I think. On some level, you can kind of relate the particles you see in that environment to the particles that we see in this cold, harsh universe. I guess the cold universe versus hot universe. You can kind of have a map for the types of particles you see in one to the other, but their properties are definitively different. And some of the particles, then there's no simple map between the two, and particularly like I think the hunk of metal analogy is apt, right? Like you can imagine because you can imagine continuously dialing down that temperature from really hot to zero. That's why you can track that. You can track that. Like imagine you slightly dial your temperature down a little bit. Then you can look at the properties of those particles and then extrapolate, right? Then you can map those out. So like every particle, like the photon, the electron, or even the proton, can have like a higher temperature analog, but only to certain limits. Because at some point, if your temperature is so high, for example, let's say the average temperature in units of energy is higher than what it takes to create a proton, then the proton basically melt because protons can get created or destroyed, and basically the proton will melt into its constituents. And I think that happens probably at a slightly lower temperature than that. But sometimes these notions of particles actually get totally destroyed. There's not even a way for you to link, from the lower temperature perspective to the higher temperature perspective, right? So it depends, I guess. Sometimes you can relate them, sometimes you cannot.
Okay, so no, I think this is a good case study, right? So let's take two particles as an example, right? Like there's the particle called the proton, which we all know, we've all heard of, and it has some mass, right? And as we discussed, uh, if you increase the temperature to a certain point where now there's enough energy in the environment to create protons, you kind of destroy the idea of the proton because now the universe can just create them, willy-nilly, like whenever it wants. So you can't even talk about like a proton being here because now there's one, now there's two, now there's one again, now there's three. Um, a photon is an example of a particle that we know about that has zero mass, right? So even in our cold temperature of our universe that it is right now, the photon is special because that one is really not well defined, right? If a photon, so if I want to say that I have 6 protons in the box, how can I know that? Well, I can measure the mass of all the stuff inside the box, and I can say, oh, that's like roughly 6 times the mass of what I know to be a proton, right? But if I have a box, how can I count the number of photons in the box? Um, it's kind of hard, right? Because I can't play the same game where I can count the mass of all the particles in the box and just translate that because the photon doesn't have any mass. So in a sense, there are an infinite number of photons in the box, right? I can just say that there's an infinite number, but they all have infinitely low energy. So
So is it because photons have no mass? What about other particles that have no mass?
yeah, it's the same. Yeah. So like a particle becomes less well defined when the temperature drops. No, the particle becomes less well defined when the temperature increases to the point where you can make these particles freely in the universe. So for a photon, that's like zero. Right? It doesn't take any energy to make infinitely unenergetic photons. So I think that's probably the best example of how this notion is ill-defined, but you just raise the temperature and everything else suffers from the same issue.
Huh. So last question I have is a little bit slightly more on the philosophical side. If the basis of mathematics is, at least I've seen applied in physics, is just counting things, and you're saying counting is not fundamental, why are you not why, but like, what would be your conjecture of why mathematics works well to even describe quantum mechanics?
That so
Totally putting you on the spot.
no. It's a really interesting question. It goes into something we were going to talk about, right? Because these kinds of quasi particles that Tim brought up earlier, they're actually like based on this strict idea of countability. I don't think we have time to get into that yet. But with quasi particles, you often can define an exact integer that defines their existence of, how many there are. And there's supposedly some duality between these quasi-particles and real particles that is, mainly theoretical for now, but there's a lot of evidence to show that these quasi-particles that are defined by the strict countability factor are dual to these things that we claim are not countable. Yeah.
I think that's a great like cliffhanger moment. But go ahead, Tim.
Yeah, I feel like there's a little bit of selection bias here. Like like why we are even talking about these concepts. Like I guess to summarize, what is a particle? To me, I think a particle is a convenient way for humans to kind of break things down to manageable chunks so that the mathematics will make reasonable sense. And yeah, in most cases, this approximation is very good, right? And we can do calculations very reasonably. So that's why the world, we can make sense out of the world using these counting, by counting particles and counting interactions, right? You can do chemistry, you can learn about high school physics and whatnot. And and to some extent, there's no other way around it. This is how we best understand that world. So in order to go deeper, we kind of have to start from this angle, right? To this angle that there are these particles, maybe they're not so well defined, but let's use that language to go one step beyond to see like, hey, maybe these particles can melt, maybe they can turn into other particles, they can get disintegrated, but let's use that language to help us understand more complicated situation. And I don't think we have a better language to almost talk about these situations, right? Like a particle is just a very useful breakdown of stuff, even in situations when they are not so well defined. So
Yes, but I do think that Sahil brought up something very interesting, which is like, the seemingly fundamental role that integers seems to play in all this, right? Like,
Yeah.
even though we can't count particles in quantum field theory, there are objects that are defined by integers. And a lot of times they look very similar to real particles. But of course, because of tunneling effects, the number of those particles can change too. But there is some kind of interesting thing that is making integers seem fundamental in this whole picture. I don't know. I wouldn't say that we have the complete story on that.
Yeah, I would agree with that. So I realize we're at the at time. So anything you guys want to say before we head out?
Yeah, I think just like I think like a lot of things is that, like in the first half of my life, like you learn that things are like very concrete notions, and in the second half of my life, I started to learn how all these things are not really that concrete, and I feel like this is just kind of the shining example. Like even a particle's existence is not something that you can count, so don't expect anything else to be that reliable.
yeah, I think that's actually a very general trend as someone who learns physics, and the deeper you go, the more you realize even basic concepts that you take for granted so much turns out to be approximate. And the same thing is true for something as fundamental as a particle, which we thought were the building blocks of everything, right? The indivisible unit that makes up everything. So unfortunately, yeah, even that thing, that particle itself is it's not well defined, but we still use it in physics. We use it as a proxy. It's just a way of language, right? It's to divide the piece of mathematics such that you can do calculation in a tractable way, right? But ultimately, even this concept itself, it's not defined. And ultimately, I guess nature probably has its own mind, right? It's probably smarter than us, and nature just is what it is. And whatever the true notion there is, or maybe there isn't one, right? Maybe everything is kind of amorphous. There isn't a fundamental unit that is indivisible that you can use to count things. Maybe there isn't. So I guess it's a lesson that we should all be humble and just and just accept the ambiguity as it is. So
I really like that.
Is that like God created the integers and the rest was the work of man? I forget who that was.
Yeah, I heard something like that as well.
There's
Yeah.
something to it. I mean, I feel like this has all been kind of like a diatribe against integers, but there's something there.
Or should we try to proclaim like Nietzsche, like a particle is dead? There's no such
No,
thing.
no, no, let's not. It's kind of cool. Let's not.
Fair, fair. Well, before we go down that rabbit hole, I'd like to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week. Bye.